All right, thank you, Christine. You can hear me okay?
Yes, I can.
Excellent. All right, so this is joint work with my master's student, Preethi, at University of Minnesota Duluth. So I would like to talk about a particular operation called majority vote. So a majority vote works as follows. If I have a collection of strings, so for example, binary strings like this, then what I'd like to do is create a new string. And so to create the new string, I'm going to allow this collection of strings to take a vote. So what I mean by that is I look in every position, and at each index, I just apply the majority function, right? So here on the slide, what I have is all of the columns that have majority zeros, I've highlighted in red, and all of the columns with majority ones, I've highlighted in blue. All right, so this allows us then to deterministically compute a new string by simply taking the majority of each position, right? So this, as you can imagine, has been around for some time in the form of crossover. So we can go back to a paper all the way in 1994 by Ising et al. And what they were looking at was multi-parent crossover. So they were interested in seeing what kinds of things we can do when we allow more than two parents to recombine. Okay, and so they came up with this idea. They called it occurrence-based scanning, but this is essentially this majority vote. So this was looked at a little bit more recently in a paper by Friedrich et al., who basically looked at the mu+1 GA, but rather than taking something like uniform crossover, during the crossover step, they select 3 parents out of the population and then apply a majority vote of those 3 parents to create the offspring. All right, and what they were able to do is show that this can solve the jump function in n log n time. So you already saw the jump function in Amir's talk. This is just a function where the algorithm has to first hill climb up to a plateau, and then it must jump over a gap of Hamming distance, in this case, k. So they showed that using the majority vote crossover, they could solve the jump function in n log n time on jump gaps of roughly square root n, slightly lower than square root n. So more recently, in a paper by Darrell Whitley et al., they showed that, well, you don't even need to sort of keep this population around. What you can do is just generate 3 strings uniformly at random, and then use a next descent hill climbing to create 3 local optima and hit the plateau on jump. And then you take the majority vote of those 3. And since you started off with random strings, and you have sufficient probability that you have good diversity among these 3 strings. And so with high probability, the majority vote is going to give you the optimal string of jump. And they show this works up to logarithmic jump sizes. So in FOGA of 2019, Rowe and Aishwaryaprajna looked at this paper of Darrell Whitley and said, well, we don't even need to do this hill climbing. We can do something even simpler. And what they showed was if you just take mu samples by performing a binary tournament in every sample. So mu times you select 2 strings uniformly at random, and then you just take the fitter of the 2, and then just return the majority vote of all those mu strings. Then you can solve OneMax in n log n time, jump in n log n time, with jump gaps all the way up to a constant fraction. You can solve monotone functions efficiently. And what's really interesting is you can solve OneMax problems that have an additive noise to them. So if you have OneMax, and in each fitness evaluation, you add some Gaussian noise with variance sigma squared, what they showed is all you need to solve it with high probability is n plus sigma squared times log n samples. And what's remarkable about this is kind of the best known time bound for this noisy model of OneMax, right? So this is a very simple algorithm, but yet it seems to do well on several problems. So we want to focus on this one, The motivation of the paper is to kind of look into this surprisingly simple effect, yet effective approach, and sort of see where it could have trouble. All right. So we conjectured that, in particular, where this algorithm would struggle is on functions that would have spin-flip symmetry. So spin-flip symmetry is essentially a function has spin-flip symmetry when it's invariant to complementation. So in other words, you take a string, whatever its fitness is, that also is the fitness of its complement. Right? So is the conjecture true? We wanted to sort of prove this. And if it is in fact true, what measures can we take to kind of modify this sampling approach in order to improve its performance on spin-flip symmetric functions? So yeah, so just to kind of look into this majority vote algorithm again, we'll call it MVA. So mu times, we sample two strings, we take the fitter of the two and we add it to the sample set, or we can call it a population. And then we finish just by returning the majority vote. So our first kind of a bit negative result is that if f is any spin-flip symmetric function that has a polynomial number of global optima, then for population sizes bounded by n to the 1 minus epsilon, where epsilon is some value between 0 and 1, then with probability approaching 1, the majority vote algorithm is going to fail. And the idea is basically is pretty straightforward. If you think about what happens under spin-flip symmetry, if you have any kind of signal, any kind of fitness distance coupling from an optimal solution, it's always going to be canceled out exactly by its complement, all right? And furthermore, because of the symmetry, so for any x, the probability that it ends up in this population is roughly equal to the probability that its complement will end up in the population. And so everything's going to kind of cancel out, all right? And so at the end, the majority correct indices, so if you sort of pick an optimal solution, the total number that are aligned, the total number of indices that are aligned with that optimal solution in those mu samples is going to be concentrated around n times mu half. And you can kind of show that with high probability, this happens, and therefore you won't have enough votes to kind of jump to that solution or any other polynomial, any other of the polynomial number of solutions. So here's just kind of an example of what I mean by this. So we'll take the function 2max. This is kind of the spin-flip symmetric version of 1max. In 2max, if you have a string, the fitness is you look at the number of ones and the number of zeros, and you return the larger of the two. And yeah, so just to kind of illustrate this, if you run this majority vote algorithm 1,000 times, for each value n, then of course when n equals 1, every string in the space is optimal. So you're always going to solve it, but very quickly as you increase n, even with a population size that's exponential in n, by the time you get to n equals 8, 9, and 10, you almost solve none of these 1,000 trials. Right? So this is because of this mirroring effect that's occurring. So we want to understand how we might mitigate this problem. And so what we did is we sort of came up with a strategy that's based on the following observation. So if you have a function with spin-flip symmetry, then that means there is a global optimum that has its first position set to 1. So if you have a global optimum that has its first position set to 0, then its complement, because of spin-flip symmetry, is also a global optimum. And so therefore, there must be one that has the first element set to 1. So if we can think of all of the binary strings in a hypercube like this, then what this means is there's kind of two subcubes that have a symmetry between them, right? So in this red subcube, all of the strings of the first element set to 0, and in the blue subcube, all of the strings of the first element set to 1. So the idea is that we sample out of this, but anytime we sample a string in the red subcube, we want to reflect it into the blue subcube, all right? So we only focus on this. And we reflect it by just taking the complement. So this leaves the fitness unchanged because of the spin flip symmetry. So for example, if we happen to sample a string like 0, 1, 0, 1 here, then we take the complement and reflect it here to 1, 0, 1, 0, right? So this allows us to just focus in here, and therefore this gets rid of this mirror across the complementation. So the nice thing about this is it's just a very small tweak to the majority vote algorithm. So we call this a symmetry-breaking majority vote algorithm, MVA. And all we have to do is, after we sample these two strings, we simply check each one to see if it's in the red subcube. And if it is, then we just take the complement, and that reflects it into the blue subcube. And then everything else remains the same. So what we're able to show is that for any mu, so mu is the number of samples, of course, greater than or equal to 8 pi squared times c plus 1 times n squared log n, this algorithm will correctly find the optimum of 2max with probability at least 1 minus 1 over n to the c, where c is the constant that we can kind of plug into this population size here. So the main proof idea behind this is that if we look at 2max, so along the x-axis here, this is just the number of ones in the string. We have what looks like this. So we have an optimal consisting of all zeros and an optimal consisting of all ones. And then we have these two branches here. And on this branch, we have majority of ones. This branch, we have majority of zeros. So what happens is when we sample, some of the strings will be in the red subcube, and some of the strings will be in the blue subcube. All right. And some of the red subcube strings will be on the majority ones branch, and some will be on the majority zeros branch. But when we reflect them, they're going to swap branches, right? So all we have to do is show that there's a slight sampling bias. After doing this reflection, there's going to be a slight bias to end up on the majority ones branch. Okay, and so as long as that's true, then all we need to do is show that for large enough mu, we have enough mass over here on the majority ones branch that the vote will direct us right to the optimum here. Okay. So looking a little bit more carefully into this proof, what we do is we consider two hyperplanes. All right, so if we fix an index k, then we call hk1 the hyperplane that has a 1 in the first position and a 1 in the kth position. And hk0, this is the set of strings with a 1 in the first position and a 0 in the kth position. All right. So if we sample x and y out of all of the strings that start with 1, so we sample out of this blue cube, then what we can do is we can bound the conditional probability that x wins the tournament, so that the fitness of x is greater than the fitness of y, given that x came out of the hk1 hypercube and y came out of the hk0 hypercube. And so we use some combinatorial counting arguments to bound this away from 1/2. Okay, specifically 1/2 plus something that's at least 1 over 2 pi n. So using Bayes' law, we can sort of turn this around and show that the probability that x comes out of this hypercube with a 1 in the kth position is also bounded away from 1/2. Okay. So, so what this can allow us to do is, if we look at the mu tournament winners, because these samples are taken independently of one another, then if we look at the number of ones and the number of zeros at index k, we can apply Hoeffding's inequality, which is this sort of well-known concentration bound that ensures that the position that will contain more ones than zeros, with probability 1 minus e to the minus mu epsilon squared over 2, right? So that says, well, as long as we set mu high enough, then we also can take a union bound over all n minus 1 of these, and this allows us to have this probability here. So if we set mu to this value here, then this immediately gives us this after taking a union bound over all of these n-1 positions. Okay. So the good news is it doesn't just hold for TwoMax. We also showed that this holds for some satisfiability problems. So particularly, we showed that there are two families of formulas, not traditional satisfiability, but exclusive or formulas, and also not all equal satisfiability formulas, where we essentially can use some arguments to show that this carries over to these problems. So essentially, we sort of set up a correlation between the landscape of these formulas and the TwoMax landscape, and then we can show that this holds. So the bad news is that it doesn't always hold, and the reason is it doesn't always hold that symmetry breaking can solve all spin-flip symmetric functions. And the reason is because spin-flip symmetric function, or the symmetry breaking algorithm, is working because there's a high structure. There's a clear signal toward the optimal, right? There's a nice fitness distance correlation on these satisfiability problems or on TwoMax. The problem is if there is a lot of neutrality in the landscape, then there's no clear signal toward the optimum, and it kind of doesn't matter whether we're jumping into the blue subcube or not, right? So to kind of show this failure case, we considered a problem that has quite a lot of neutrality. This is called the one-dimensional Ising model, or Ising model, named after physicist Ernst Ising. And essentially what it is we have a graph, in this case a cycle graph, on n vertices. So each vertex corresponds to one of the elements in our string. And what we want to do is we want to minimize the number of edges that are incident to vertices that have two different values. Okay, or in other words, we want to maximize the number of edges that have the same value, either 1 or 0 between them. Right. So you can imagine there's quite a lot of neutrality on this landscape. And so here's what we were able to show, that if n is even, then for any mu, so for any population size, this symmetry breaking majority vote algorithm will fail to generate an optimal solution on this 1D Ising model with probability that's sort of exponentially approaching 1. And so the basic idea behind this is that, well, there is no bias now. There's no bias towards this hyperplane HK1. So at particular indices. So if we let x and y both be drawn out of this blue subcube, then if we choose any of the odd indices, we essentially can show that the probability that x is going to be the winner, given that x came out of the HK1 hypercube and y came out of the HK0 hypercube, is equal to 1/2. All right, so we've also used some counting arguments to show that these two things are exactly equal. So the probability x wins, given that they came out of different hyperplanes, is equal to the probability x wins, given that they came out of the HK1 hyperplane, and that equals to 1/2. So applying law of total probability, we can show that the probability x wins, given that its kth position is 1 is 1/2. And applying Bayes' law, we can just plug this in 1/2. Its probability that xk equals 1 is 1/2. Probability it wins is also 1/2. And so this means that the probability that there's a 1 in the position of the winner is exactly 1/2. So that means that at every odd index, the distribution of 1s across these mu individuals is symmetric around mu1/2, right? So that means that mu1/2 is the median of this, and it means that the probability that this is that the majority becomes 1 is exactly 1/2. And so we need it to be all 1s at every string, at every position. And so therefore that's going to kind of vanish. The probability of that nice thing happening to us is going to go away very fast. Okay, so I just want to kind of go over some experiments that we did to look at these bounds here. So on the left-hand side here, we see that for TwoMax, what we did is we generated or we ran this algorithm several times each, and we sort of looked at n moving from 100 to 300, and then we tried to see, well, what's the dependence on being able to solve the problem on the actual sample size, the population size, right? And so, yeah, so as you can see, when mu is very small, then we don't solve anything, but this is kind of very quickly transitioning into a phase where we can solve everything. And of course, that's going to depend on n. The main thing that I kind of want to point out here is that if you look at this red vertical line here, this is corresponding to 8 pi squared 100 squared times log 100. All right. So this would be the sort of our first theorem with c equals 0. So kind of the trivial probability bound for n equals 100. All right. But as you can see already, for n equals 100, we have a very low mu, like order of magnitude lower, is already solving most of them. So what this is suggesting is that our bound is not tight, and we actually conjecture that this can be improved by a factor of n. But this is future work. And then just quickly, we also looked at randomized versions of these SAT formulas. And we wanted to sort of see what's the dependence on the fraction that are solved by the symmetry breaking majority vote algorithm, depending on the constraint density. And you can sort of see that for one model, it very gradually goes up to 1. And then for another model, it very quickly jumps up to 1. All right, that's exclusive OR versus not all equal. Okay, so just to conclude then, the majority vote algorithm is interesting. It's simple, but it performs really well on noisy OneMax and jump. So we were able to prove that it fails to solve spin flip symmetric functions because of this sort of mirroring effect that we see. But we also introduced just a tiny modification that breaks the symmetry that causes a problem. And this results in a performance guarantee for easy spin flip symmetric functions like TwoMax and variance of propositional satisfiability. We proved that it can't handle highly neutral landscapes like the 1D Ising model. And just for future work, we'd like to extend these results to noisy TwoMax because we have a feeling that it would probably work there, and also to symmetric jump functions. So that is all I wanted to talk about. Thanks very much, and I'm happy to take questions.
Thank you very much, Andrew, for this interesting talk. And are there any questions from the audience? Okay, let me start again. This spin flip symmetry. So you mentioned that the set formulas you considered, they have this property, obviously, and the Ising model has the property. Are there any other problems? Is that a common property of combinatorial optimization problems? So
yes. So if you think of things like graph coloring, if you, I mean, there's lots of different sort of problems on graphs where, yeah, you have some kind of you're trying to make some kind of a selection of a set, and or a number of sets, and if you do some kind of a complementation or you do some kind of permutation on the symbols or something like that, then you sort of come up with the same evaluation function. But this is, so the spin flip symmetry has been around for some time, looking at, I think empirically, looking at different problems. I think it was maybe in a paper by Goldberg or something like that early on, who said that this would also pose a problem to things like regular genetic algorithms for the same kind of reason, that there's this, if you're doing crossover, you cross over something, on one, like for example, TwoMax on one branch of the of the TwoMax function with something on the other branch, then you're going to end up with something with really poor fitness. So, anytime you have this kind of thing going on, then this is an issue.
So there is quite some potential to look at this algorithm in the context of other combinatorial optimization problems and maybe use some of the insights for this. Okay.
I would hope so.
Okay, that's pretty neat idea. Okay, are there any other questions? Okay, if this is not the case, then first of all, thank you very much again, Andrew, for this talk, and also thanks a lot for all the 4 speakers of this session.